Hello everyone. Today we will have a look into magnetic methods of investigation. Right? What is magnetism? Force a magnet exerts on a piece of iron, or the force of Earth's magnetic field exerts on the magnetic compass or a needle of the compass, are the classical examples of magnetism. All of us have an experience of magnetism. How? During our childhood, most of us have played with the magnets. One of the common thing which we do is we used to use the magnet, right? We used to just keep it over the sand, try to collect all the fine iron dust, and we used to separate the iron dust on a paper, on a sheet of paper, and we used to hold the magnet below the paper, and we used to play and see how this iron dust or iron fillings are dancing, isn't it? All of us have played. That is a classic example of Earth's magnetism. And also most of us have used a magnetic compass. However, today we are not using that often, right? We would have used, some of you would have used magnetic compass. That is another classic example of Earth's magnetism, right? The magnetic field has got both intensity as well as direction, right? It has got both intensity and direction. We will understand that slowly, right? The strength of the magnetic field or magnetic force, when you measure the strength of the magnetic force at the surface of the earth from a particular location, the magnetic force which we are going to measure depend on three things. One is the amount of magnetic material that is present below that particular area. Number two, what is its distance from your instrument. Number three, what is its direction from your instrument, right? Suppose you are above the surface of the earth, here you have deployed your instrument to measure the magnetic force, and the measured value here depend on what is the magnetic material that is present. Magnetic material that is present. That means whether you had too much of magnetic material present below the surface or less amount of magnetic material. What is the distance from your sensor? What is the direction? Are you just above or your instrument is somewhere here? In which direction it is? Is it towards north, south or east or west? These things control the strength of the magnetic force which we measure at the surface. Earth's magnetic field is caused by the movement of partially molten iron in the core of the earth, especially in the outer core of the earth, right? That is what is creating the Earth's magnetic field. Since we are going to measure the naturally present Earth's magnetic field, this method is a passive method. In active method, we will send some signals and study the response of that, whereas here we are not going to transmit any signals, we are going to just measure the natural magnetic field. So, it is a passive method, right. What is the unit of measurement? Unit of measurement is Tesla, right. Magnetic field strength is measured and the unit is Tesla, referred by the capital letter T. However, in exploration or in magnetic investigation, magnetic method of investigation, the value of Tesla is too large for us. Hence, we use a much smaller unit known as nano Tesla, which is 10 power minus 9 times of Tesla, right. Equivalent to this in CGS unit is known as Gauss, referred by capital letter G. 1 Gauss is equivalent to 100,000 nano Tesla. Okay. In CGS unit equivalent to nanotesla, 1 nanotesla is equivalent to 1 gamma, right. So, these are the units which we often use. Many a times if you are following the SI unit, we will use the nanotesla, right. Another interesting feature on the surface of the earth is the magnetic intensity, total magnetic intensity. What is total magnetic intensity? We are going to see soon, maybe in the next slide, right. The magnetic field intensity on the surface of the earth vary from nearly 24,000 nanotesla to 70,000 nanotesla, right. Actually, we are continuously monitoring how the Earth's magnetic intensity varies with the help of this FARM satellite launched by the European Space Agency, right. So, I had looked into this website couple of weeks back, that means in October 2024, and this is the variation in the Earth's magnetic field. If you look at the scale, all the blue colors are of less magnetic intensity, around 2000 nanotesla. All the red color, dark colored is about 60,000 nanotesla. That is what I have indicated here. So, in the equator region, right, the values are very less, whereas in the poles, north and south pole, the values are much higher. Why is it? It is because of the difference in the diameter of the earth. Diameter of the earth is much larger, longer along the equator, whereas it is shorter between the poles. Between the poles, the diameter is shorter at least by 40 to 45 kilometers. So, due to which magnetic intensity is much higher in the poles, at the poles, whereas it is lower at the equator. Now, let us have a look into what we are going to measure in the magnetic methods. The geomagnetic field can be understood from this diagram. Before looking into this, let us have a look into how a freely suspended magnetic needle in a thread will behave, right. Suppose if you suspend a magnetic needle in the thread in the northern hemisphere, the magnetic needle will point downwards, right, little bit downwards toward the magnetic north, right. Suppose if you consider this as a magnetic needle, right, this is the magnetic needle in an axis horizontal to the earth's surface, right. If you orient this towards north south, right, towards north south, if this is north and if this instrument is kept in the northern hemisphere, this will point downwards in the north, right. And in southern hemisphere, it will dip upwards, right. In the northern hemisphere, the needle will dip towards north, whereas in southern hemisphere, the needle will dip upwards towards the north, right. At the pole, if you take this arrangement to the pole, it will remain vertical, the needle will be vertical. How about in the equator? In the equator, it will be horizontal. We had already seen the total field vector will vary from 24,000 to 70,000 nanotesla. Right. Let us see how it will vary. So, this is what we were discussing. So, when you have the needle tied to a thread, right, when you are here, the needle will be dipping towards north, as you see in these arrows. somewhere here it also dips towards north, but the angle is much more. Somewhere here the angle increases. When you are here, the magnetic needle is essentially vertical. When you are at the equator, the needle is essentially horizontal. When you move this way, right, again the reverse will happen. Somewhere here it is essentially vertical. So, this is how the angle of inclination vary when you hold a magnetic needle tied at the center, right. So, that means this is the magnetic needle, right. If you attach it to a thread should be exactly at the middle of the magnetic needle. So, this is how the magnetic needle will behave, right. Now, let us have a look into what are all the different components of magnetic field, right. So, I will try to explain that with this small diagram, right. First is the magnetic inclination. What is magnetic inclination? We were discussing when you are having a needle tied to a thread, that means the center of your needle is tied to a thread. Imagine this is the needle now, right. This is attached to a thread. We were discussing depending upon where you are, the needle will point downwards or upwards, right. So, that angle is known as I, which is known as inclination, right. I is the inclination. So, what is I? I is the angle that the magnetic needle is going to make when you keep it at a particular location. The needle can be freely suspended. Imagine we are freely suspending the needle, so that we need not worry about the axis of the needle. Suppose if you freely suspend the needle by holding it by connecting a thread at the center, right. So, this is the magnetic needle attached to a thread. Okay. It is going to point, let us say, point downwards, as you see in this diagram. This angle is angle of inclination. Is that clear? Now, what is declination? That is number 2. Declination is the projection of this magnetic needle to a horizontal surface, and on the horizontal surface how much angle it is away from the geographic north, right. That is known as declination. Hope you can understand, right. This is the direction of the magnetic needle. You project this to a horizontal plane, the projection is this, and what is the angle it makes with the geographic north, that is known as declination. Is it clear? Right. That means I am drawing it here. This is the inclination. This is how the needle is oriented now. The projection of that on a horizontal plane is the red line which I am drawing now. What is the angle that it makes from the geographic north is the declination. So, these two are angles, right. One is inclination, second is the declination. Then let us see this particular line. So, the needle is inclined and it is attracted toward the earth, right. So, what is that vector? That is known as total field. So, the B is known as total field, right. So, B is the total field vector, and for this total field vector there will be two other components. What are they? They are horizontal and vertical components. So, the horizontal component is this, that is referred by letter H, and the vertical component is this, that is referred by letter Z, right. So, the total field vector has two components in x direction and y direction, or sorry, in z direction, right. So, the one along the x direction is known as h. That means, at the projection of that on a horizontal plane, that is z, the projection or the resulting force in the vertical direction is known as z. So, these are the three vectors. One is B, that is the total field vector. This is what we had seen when I showed the image of swarm data, right. So, here I mentioned we are going to see what is the total intensity. So, this diagram shows the total field intensity, that is what is referred as letter B in this diagram, right. This is the total field. So, in magnetic investigation, we can measure any one of these 5 components of magnetic field. It is interesting, isn't it? That means, we can measure either inclination or declination, or horizontal component, vertical component, or the total field vector, right. But conventionally, mostly we are measuring the total field vector, right. But however, we can measure any of this, right. Now, after seeing some introductory aspect, let us move on to magnetic exploration, right. So, in magnetic exploration, what we are going to do is, we are going to study the subsurface by measurements of magnetic field or its components. We have seen 5 components on the previous slide, right. You can measure 2 or 3 components or just one, right. So, we are going to measure the components of magnetic field at the surface at different locations over our area of interest to understand about the subsurface. So, this is what is magnetic exploration. So, what we are going to do? We are going to deploy an instrument, measure one or more components of the magnetic field at different locations over the area of our interest to understand about the subsurface, right. The survey depend on the Earth's magnetic field, because we know Earth itself is functioning like a large magnet. So, the survey depend, or our investigation depend on Earth's magnetic field, right. How? The Earth's magnetic field resulting from magnetic properties of the rocks present below the surface, right. Imagine you are at the surface, right, you are standing here, right, and making a measurement of Earth's magnetic field. The magnetic field which you measure is a result of the Earth's magnetic field as well as the magnetic properties of the material that is present just beneath you. What are the properties? One is susceptibility and the other one is remanence, right. So, why we are going to do this exploration? To locate magnetic materials, also to determine depth to the basement rock. Suppose if you are a geotechnical engineer and your interest is to know where the rock is from the ground surface. So, these are the major aims of magnetic exploration, mainly to locate magnetic minerals or to understand about the subsurface configuration, right. And in fact, magnetite is the only natural mineral with obvious magnetic properties, right. Why we are looking into this is, we were saying the magnetic field intensity which we measure on the surface depend on the Earth's magnetic field as well as the magnetic properties of the subsurface below us, isn't it, below the point of measurement. See, magnetite is one of the mineral, or in fact, this is the only mineral having obvious magnetic properties. Then iron. because of its atomic structure. We had played with iron dust only with the magnet, right. Because of its atomic structure has got the tendency to become magnetized. We had actually played with, we used to attach a iron nail or iron pin with the magnet for couple of days. Then after removing the iron nail from the magnet, the iron nail itself is able to function like a magnet for few hours at least. So, iron has got the tendency to become magnetized. Like iron, other elements are cobalt and nickel also has got some tendency to become magnetic, right. So, one is magnetite, it is a mineral which is distributed widely. Iron is an element which is also found in different minerals. Apart from iron, cobalt, nickel, they are also present in different rocks, right. So, minerals and rocks which contain any of this are likely to be more magnetic. What is any of this? 1 is magnetite, 2 is iron, 3 is cobalt, 4 is nickel. If the rocks present below the surface are the rock containing minerals having cobalt, nickel or iron, they are likely to be more magnetic. Okay. So, magnetic strength of the mineral or rock therefore depend on the amount of iron, nickel, cobalt and also the amount of alignment along which they occur in the minerals, right. So, the measure of magnetic strength of a mineral or rock is called as magnetic susceptibility, right. Measure of magnetic strength is magnetic susceptibility. This can be measured qualitatively. We have done during, all of you would have done this qualitatively. You will measure the susceptibility by taking a magnet towards a gun pin or towards a safety pin. If the safety pin has got large amount of iron, pin quickly gets attracted toward the magnet. If the pin is having very less amount of iron, you need to take the magnet very close to the pin to attract the pin, isn't it? So, that is what is susceptibility. This can be measured qualitatively with a simple magnet, right, by testing the pull. If the pin quickly gets pulled from a greater distance by the magnet, then it is highly susceptible to magnetism, right. So, here in magnetic investigation, we are going to use a meter or a instrument that is called as magnetometer, right. So, magnetometer is the instrument that is going to be used by us to test the or to determine the magnetic susceptibility, right. Susceptibility of a completely non-magnetic substance, right. In fact, no naturally present material is completely non-magnetic. If you assume a completely non-magnetic substance, then susceptibility is 0. Susceptibility for a highly magnetic mineral such as magnetite is about 20. So, the value of susceptibility will vary between 0 to 20, but as I told you, every mineral has got at least some minor amount of magnetic susceptibility. Okay, why? Because they may have magnetite or any mineral may have little bit of iron, cobalt or nickel, due to which they have some magnetic susceptibility. So, what is magnetic susceptibility? Which is a measure of magnetic strength. So, magnetic susceptibility can be given by this equation where I is the induced magnetism and H is the magnetic force and K is the magnetic susceptibility. Magnetic susceptibility does not have a unit, and as usual we used to look into the susceptibility of different naturally occurring materials. So, here is a table that shows the magnetic susceptibility of different materials, right, different rocks, right. Magnetic susceptibility of different rocks are shown here. As you can see, basic igneous rocks has got very high amount of magnetic susceptibility, whereas other rocks, sedimentary rocks, are having very less magnetic susceptibility. Okay. And the range of values given for each material depend on amount of magnetite or other susceptible elements that are present in the rock. That we had seen this already, right. And the rock containing, interesting thing is, rock containing just 1% of magnetite may have susceptibility as large as 1000 times than most rocks. Okay. Even if the rock has got 1% of it is magnetite, then its susceptibility will be 1000 times more than the rock which do not have magnetite. So, that is why any naturally present mineral and rock, naturally present material which are minerals and rocks will be magnetically susceptible. So, in this lecture today, we started looking into magnetic methods of investigation. In the beginning, we had seen two examples of classic examples of Earth's magnetism. One is the magnetic compass, other one is we had played with the magnet, how magnet attracts magnetically susceptible materials which are iron. These are the two classic examples. Then we had seen the unit of measurement. Unit of measurement is nanotesla. After having looked into that, we had seen how the total magnetic field strength varies over the surface of the earth. It is little comparatively less at the equator, very high at the pole. After that, we had started looking into 5 components of magnetic field. Out of the 5 components, usually we measure the total field vector, that is B, is the one which we often measure. In magnetic exploration, we are going to measure the total field vector B or any other components on the surface of the earth at different points, and the value which we measure is dependent on the amount of magnetite that is present below the surface, or iron, cobalt and nickel. These 3 elements are magnetically susceptible. So, their composition in the earth will affect the value which we are going to measure at the surface. Right. Then we had a look into magnetic susceptibility. Magnetic susceptibility can be estimated using this equation. This table gives how the magnetic susceptibility of different geological material vary. We will continue further on the application and other aspects of magnetic methods in the next lecture. Thank you very much.